Welcome to Online Algebra 2. Today, we'll be talking about section 7-2, properties of exponential functions. So in this section, our objective is to first explore the properties of functions in the form y is equal to a times b to the x power, and then graph and do some problems with special exponential functions that have a base of something called e. And basically what we're going to try to talk about in this section is that the factor of a, this thing right here, can stretch or compress and reflect the graph of the parent function. And in fact, all of the other four types of transformations that we can do, stretches, compressions, reflections, and translations, we can do them all to exponential functions as well. So if we add something to the outside of the exponential function, it's going to go up. Subtract, it's going to go down. Inside the exponential function, we're going to shift it right if it's a minus, left if it's a plus. A number bigger than 1 in the front is going to be a vertical stretch. A number that is between 0 and 1 is going to be a vertical compression. A negative in the front reflects in the x. A negative inside the function reflects in the y. So all these translations pretty much are going to do the same thing that we're used to from all the other types of functions that we looked at. The only difference is how the function actually looks when you're moving it around. Okay, so if we look at this as the parent function, the red one, and then we look at this function, 3 times 2 to the x power in blue, you can see that this has been, each dot has been stretched, right? It is further, and then the distance is not translated, right? It's not moving the red line up, right? Each point, as you go further right, each point gets further and further away from the one you're stretching it, because you're stretching it by a factor of 3, okay? So it's 3 times the corresponding y values if you look at the table right there. And, right, that's what it says, stretched by a factor of 3. So if we look at this function, negative 1/3 times 3 to the x power, this is my parent function. So y is equal to 3 to the x power is the thing that I am going to compare this to. Let's just graph this real quick. So y is equal to 3 to the x power. So that's going to be 1, right? I'm just plugging in numbers, right? 3 to the 0 power is 1. So here's my first point. Here's my second point. Here's my third point. 2 squared is 9. 9. And then as I go into the negatives, right, that becomes 1/3. And, right, I have my exponential function that'll never go below 0. So I get my graph that looks kind of like that. Different than this function. So when I graph negative 1/3 times 3 to the x power, right, if I make a table again, right, if I start plugging in numbers, that is 1 times, that's now negative 1/3. So instead of being up here, now I'm down there. Okay, if I plug in 1, I get 3 times negative 1/3, that's negative 1. If I plug in 2, I get 9 times negative 1/3, that's negative 3. So I think you can see that now this function has been reflected and it's also been compressed. Look at this one. This is, 1. This is only 1/3. So this is going to be kind of similar back here, but obviously different as we go down this way. Okay. So we can do this with any type of functions. We can look at what's going on. Here's my parent, 5 to the x power. So that's 1, 5, and then 25. And we get my graph just by plugging in points. And then to get negative 1/2 times 5 to the x power, right? If I make my graph here, again, same concept, negative 1/2. Plug in 1. That's now negative 5 over 2. Plug in 2. That's negative 25 over 2, 12.5. Okay, so we get negative 1/2, 2.5, 12.5, right about there. And we get a graph that kind of goes eh, not terribly not terribly nice, but we get the idea. Okay, so stretch compression and reflection, if we remember those. Horizontal shifts and vertical shifts can be a little confusing. So a horizontal shift is the same as the vertical stretch or compression, which looks like this. So if you sort of split this up, if we remember exponent rules, right? Same base. If you're subtracting, right, you can just add these two exponents together and get x minus h for the exponent. And so um, if we take this term right here and just multiply it by a times b to the negative h, we would get the same thing. But an easier way to think about it is just that it shifts the function left or right, and then this one shifts the function up or down. And notice that this is inside the function, so that would be a horizontal shift. This is outside the function, which is a vertical shift. And the important thing with a vertical shift is it switches the asymptote. If it moves the function up, the asymptote is going to go up. If it moves the function down, the asymptote is going to go down. Okay, so I could do something weird like the beginning of that problem and say that this is the same thing as y to the 2 to the negative 4 times 2 to the x power, but that's kind of strange. Okay, so I would rather just realize that this exponent shifts the function right 4. So if I was looking at this function, which is the parent function of this particular exponential function, I would get, right, 2, 3 times 3 times 3, 6, 7, 8 is 8. And I would get something that looked like this. Now to graph this one, now when I plug in x and y, right, I would get, that would be 2 to the negative 4 power, which would be 1 over 16. When I plugged in 1, that would be 2 to the negative 3 power, which would be 1 over 8. When I plugged in 2, that's 2 to the negative 2 power, which is 1 over 4. I would have to plug in 4 in order to get 2 to the 0 power, which is 1. So at 4, this function is 1. Okay, and as I'm going left here, I'm getting fractions. If I plug in 5, now that's 2. If I plug in 6, now that's 4. And if I plug in, oh, I made that one a little bit wrong, right? 1 is 2, 2 should be 4, and then 3 should be 8. So that was a little off. Okay. And then this one, 5, 6, 7 would be 8. So you can see all these points have been shifted to the right 4. Okay. With this one right here, okay, so as I look at this function, all right, I know that it's going to be exponential decay, and then that the graph is going to be shifted up 10 and then stretched out by a factor of 20, right? But the easiest way to do this then is, of course, to just set up a table, okay? If I plug 0 into this table, 1/2 to the 0 power is 1, so that would be 30. If I plugged in 1, 1/2 to the first power is 1/2. Half of 20 is 10. So that's 20. So 1 is 20. And you can see this is going to dive down pretty fast. If I plug in 2, that's 1/4. That would be 5, so that's 15. Um, yeah, halfway. Yeah, whatever. Good enough. Let's plug in 3. So now that's 1 over 8, which is 2.5. So we get 12.5. So this is going to be kind of hard to graph right there. All right, and what's happening is that the graph is sloping down and it's going to flatten out at my new horizontal asymptote, which would be 10. That's 12.5. Let's plug in a -1. So that turns this into a 2, 40, 50. And the next one's going to be way off the graph. So we can see that we get a graph kind of like that, and it flattens out as we hit 10, not 0, 10, because the function has been shifted up 10. Let's just look at these real quick without graphing them. This 2 shifts the function to the left 2. This is a vertical stretch, and this tells me that is growth. This tells me that this is a decay, and that the function has been shifted up 5. So the base, this base has nothing to do with the transformation, right? It doesn't change what the function is actually doing. All it does is tell you whether the function is being growth or decay, and it is its own parent function, right? This 4 and this 0.25, we can never change the 4 to a 0.25, right? These are going to be two different functions independent of each other. Okay, so that, while that is all interesting, we can have what our transformations of exponential functions kind of look like. Here's my basic function. Whatever the base is, that's my parent function. If I put a number in the front here, if it's bigger than 1, it's going to stretch vertically. If it's between 0 and 1, it's going to compress vertically. And if it's negative, it means that it's reflecting in the x-axis. And then this is left or right, that's up or down. This is every transformation together in exponential form. All right. So with all these, we can graph many different types of functions. Okay. Now, let's just go right here. The most common base in our number system would be 10. And in fact, there's a whole type of number with a base 10 that you probably know how to use, scientific notation. Okay, right? So we would write in scientific notation 3 times 10 to the 5th power, right, to write really big numbers. So we do a lot of stuff with base 10 exponents. There's another base that is also very common, right, but not very well known. So up until this point, all the numbers that we work with have been rational. All the bases are rational. One of the exponential functions that has an irrational base is very common. So if you look at this graph right here, y is equal to 1 plus 1 over x to the x power, if you were to graph that out and you start plugging in numbers, you plug in 2, you get 2, or if you plug in 1, you get 2. If you plug in 10, you get 2.5. You plug in 100, you plug in 1,000, you plug in 10,000, million, whatever. As you start plugging bigger and bigger numbers, as the graph goes towards infinity, as the graph goes right, it approaches a value of 2.71828, also known as E. Okay, standing for Euler's number. Okay. This number, E, is very common in graphing continuous exponential growth. Okay, and we actually call it the natural base. Okay, so this natural base of E is very useful for graphing continuous growth or decay. Right, and these functions have the same functions as other exponential functions. And you should be able to use your calculator to evaluate it. Somewhere on your calculator, there is a button for E. You're going to have to find it, okay? Depending on the type of calculator you have, I would look for something like this, LN. We'll talk about that in a later section. Usually it's above it. You might have to press shift to get to it. All right, but somewhere on your calculator, there should be a button, hopefully that looks like this, or maybe like this, and that means that you can take E and raise it to an exponent. So on my calculator, right, it looks just like this one, and if I wanted to calculate E to the third, I would get 20.0855. Okay, so take a minute to figure out where E is on your calculator because we're about to start using it. Okay. All right. So in section 7.1, the previous section, we studied how interest was compounded annually or quarterly or monthly. There's another type of compounding we can do, something called continuous compounding. And the continuous compounding formula is right here. Okay? Usually remember it by just saying PERT. P-E-R-T. Principal. E is my new constant, 2.7, but we don't use that, right? Just like we try not to use 3.14 for pi, right? We try to find the actual pi button on our calculator. It's the same thing, right? We should be able to find the E button on your calculator. Same idea. P, E to the RT power. Interest rate, annual interest rate, and then time in years, or monthly interest rate, time in months, whatever. Okay, as long as these two time frames match. Right? Normally we would see years, however. Okay, so let's try this. Suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest, compounded continuously. That's the word you're looking for. Right? If you see monthly, you would use a different formula. If you see annually, you use a different formula. If you see continuously, you would use this formula. So your total amount is going to equal PE to the RT power. So my amount that I have is going to be 3,000 times E. That's the interest rate. Write it as a decimal to high school 4 years later. So we do 0.5 times 4. Okay. Plugging this into my calculator. Most of the time, you can just plug this in all at once. If your calculator is not that good, you might have to multiply these two together first, but you should be able to raise E to this whole power, and you should get 36, 64, and 21 cents. Okay. Round to the nearest dollar, so just 36.64. All right. 4 years later, 4 years after high school, so now it's a total of 8 years. So now I just change my 3,000. We're still getting 5%, but instead of 4 years, now we have 8 years. We got $600 more for 4 years. Let's see, 3,000 E to the 0.05 times 8 power gives me 44.75 and 47 cents. Okay, so you do get a little bit more, right? It's not just another 600 bucks, right? Because we're continuously compounding. We're compounding interest on top of interest. My final answer is a little bit bigger. Last thing I want to talk about is something before we jump into Half-Life. Let's think about the 3 interest formulas that we talked about. There's this one, right? This one works when you're only compounding once per year. This one works when, when we compound more than once per year. Now these two formulas are pretty much the same thing, except in this case, n is 1. Okay, so we can just get rid of it. All right, this would be monthly, quarterly, daily, once a minute. Doesn't matter what n is, right? As long as you know how often you are compounding the investment or whatever, right? We can use one of these formulas. As soon as you see continuously, we do this, okay? Now, we can take this idea and use it for something like this, half-life. Looks confusing, but this is the same thing. N sub 0 is your initial amount. This is your decay rate. If you don't know what half-life means, it's for radioactive materials. It means the amount of time it takes for half of the substance to decay, to go away. So if my decay rate, if my rate is negative 50%, right? If I'm losing 50% each time, then 1 plus the rate would be 1 minus 0.5. So that would make my base 0.5, 1/2. Okay, and then total time divided by the number of half-lives. How many times do you cut this thing in half? Okay, and this is not t to the 1/2 power, right? This is t sub 1/2. It just means the half-life of the decaying quantity. All right, so let's set this up. The half-life of a radioactive substance is the time it takes for half of the material to decay. This is just the name of the phosphorus element. So phosphorus 32 is used to study a plant's use of fertilizer. Half-life, 14.3 days. How many milligrams remain 92 days if you started with a 100 milligram sample? So the amount that's left over is going to be your initial amount times 1/2 to the t over the half-life. Okay, so my initial amount was 100. That's 1/2. Total time was 92 days. Half-life was 14.3 days. 92 divided by 14.3. We raise 0.5 to that power and multiply by 100, and we get that there are 1.16 milligrams left after 92 days. There's another 14 days, there'll be half of that. So it never really goes to 0, but eventually it'll be such a small quantity that it'll be too hard to measure. Okay, so interest, half-life, population growth, depreciation, these are all types of problems that exponential modeling and exponential functions can help us answer. Okay, so let's wrap this section up. The transformation, this would be a reflection and a vertical stretch. This would be a vertical compression. This would be a shift to the right 5, and this would be a shift up 3. Okay. Is this a natural base exponential function? Yes, because it has e as the base. And this problem we can is investing 2,000 in account that pays 5%. Compounding continuously is the same as investing 1,000 at 4% and 1,000 at 6%, each compounded continuously. Probably not. We would have to actually do the calculations to see. It would never be quite exact, I don't think. But who knows? You'd have to calculate it to see which one give you more. Maybe less money over time. Over time, less money at a higher interest rate will give you more money, but probably not anytime soon. Okay, so that was 7-2, properties of exponential functions.